Hey everyone, good morning. So last time we had finished talking about programmed I/O and loading and storing I/O registers, and then bit twiddling, which is extracting bit fields out of I/O registers and setting fields within I/O registers. So that sometimes that's called bit manipulation. Other times people call it bit twiddling. We covered various ways to do that, and you'll have to do that quite a bit on the ESP32 whenever you do low-level programming, as opposed to using the pre-written APIs. Any questions about any of that stuff? That makes sense? Okay, so in this lecture, I'm going to jump around to a couple different topics, so it'll be a little disjointed. So the first thing I'm going to talk about is how to effectively get an analog signal out of the ESP32 using pulse width modulation. And then we're going to switch gears and talk about interrupts. Now remember, I mentioned that when you use programmed I/O, that is fundamentally how the software communicates with the hardware. But the model is that the CPU is the master and the peripherals are the slave, in the sense that the CPU is the only entity that can initiate communication. And so that's a problem if you have a peripheral that needs to communicate with, has a need to communicate with the CPU at some point. And so for that, we use interrupts. And then I'm going to switch gears again and talk about how the CPU communicates with external peripherals using protocols. Now this part is a little, maybe a little confusing. So when I say peripherals, I mentioned in the first lecture last Tuesday that we have these onboard peripherals. And so when you use programmed I/O, you're communicating with these onboard peripherals. The onboard peripherals are things like timers as well as interfaces that go off chip. Once you go off chip, then there's a different way that communication is done, and that's through, in this case, or in these types of systems, these low power platforms, we typically use serial I/O to go off chip, to go external. Okay, so the programmed I/O is a parallel interface that typically goes through some kind of on-chip interconnect. And so when you do a load or a store, and again, when I say load or store, that's from the assembly level perspective. From your C perspective, you're using those intrinsics, or dereferences. Makes sense? So when you're doing on-chip communication to these on-chip peripherals, you're using programmed I/O, which is a parallel interface. You're reading and writing one word, which is a 32-bit value, in one cycle, right? Essentially, right? But once you go off chip, then we have, usually you go serial. Now, why is that? Well, I mentioned that the ESP has 48 total pins, 40 of which are programmable. 40 pins is not enough to do a serial protocol, right? Because a serial protocol needs 32 pins just for the data alone, and then additional pins for control and addressing and that kind of stuff. Now, you could potentially reuse the same pins for address and data, but there's just the point is that there's not enough pins on the ESP to do a parallel interface externally, right? But internally we can. So all this programmed I/O stuff is internal. Does that make sense? Okay, so when I say peripherals, I could be referring to an on-chip peripheral or an off-chip peripheral, like something on the circuit board that the chip is talking to. Okay, so and when I say intrinsics, by the way, I'm referring to these guys. There's 4 intrinsics that we're going to use in this class. Reg read, which you just pass an address to, and it returns with the data that you want to read, right? The data being the contents of the I/O register, right? And the address is the I/O register address. Reg write doesn't return anything, but allows you to send in an address and a value that you want to write. And then you have reg set bit and reg clear bit, which are used for writing fields inside of a value, an I/O register value that you've previously read. Well, actually, this includes the read part. So included in these intrinsics, you read the old value of the I/O register based on its address, and then you manipulate a bit field, and then you're writing it back. So all of that functionality is included in these 2 intrinsics, but you have to still do the shifting part. So for example, if I want to set bit, I pass it the address of the I/O register, and then you have to, like for example, if you want to set 1 bit, I would take a 1 value and shift it 3 bits to the left to put it into bit position 3. Does that make sense? Now you might say, well, why? I mean, why is that unusual? Why do you think that's remarkable? Well, because it would be theoretically possible for this function to just allow you to set the bit number, right? But instead, it's kind of this hybrid approach where you still have to worry about this shifting, right? You still have to take 1 and shift it to bit position 3, and then you call reg set bit. So what I'm describing is kind of, what I'm trying to explain is what the interface is here, how you interface with this function, right? So if I want to set bit 3, I still have to take a 1 and shift it by 3 bits to the left, but I don't have to worry about reading the value from the I/O, doing a programmed I/O read, and then sending the value back, right? That's all taken care of for you. Does that make sense? Seems like I'm not explaining that very well, but that's essentially the interface. And then for clearing, you can do now when you clear. In this case, I'm clearing a 3-bit field whose least significant bit is at bit position 12. Now check out this syntax here. What's going on here? Well, okay, this is C, and normally in C, you don't have binary literals, right? But you can actually do that using this syntax: 0, B, lowercase b, 111. That means binary 111. Did you guys ever see that before? You've seen that before? I just learned about that myself just a few years ago, that you could do that. Because normally I would have, otherwise you'd use like hex, right? But you can actually put binary numbers in C using the 0B prefix, right, for the literal. Okay, so 0B111 is, the value 7, binary value 111, and then I'm shifting it 12 bits to the left, which means that these 1 bits are the bits that I'm going to clear. So I'm going to be clearing bits 12 up to 14, or 14 down to 12, right? Does that make sense? Now you might say, wait a second, before you showed that there was some kind of a tilde there, or a logical negation. Yes, yeah, you don't need that for if you're using this reg clear bit literal. It does that for you. You just send 1s in that you want to clear, and it does the logical negation for you, right? Does that all make sense? So you can use these. These are kind of like helper functions, right? You can use these, or you can do it with the method I showed you last week as well, right? Okay, I hope that's clear, right? So you've got these 4 helper functions that are, and I call them intrinsics because these 4 functions are mapping to specific, assembly instructions, right? In the case of reg read and reg write, this is a load, that's a store, and these guys are a little bit more complex because they include the extra steps there for setting and clearing bits. Okay, Right, so okay, so let's jump to the next topic here. So, oh yeah, one thing, one other thing. Quiz 1 is posted on Blackboard, and you just take it online. You get 2 attempts. It's just 7 questions, pretty easy, multiple choice. Just log into Blackboard sometime between now and Friday at 11:59 p.m. and make sure you take the quiz. Okay, you get 2 attempts, and the one that gets recorded is the higher score of the 2 attempts, and you get the score right after you take it, right after you submit it, and you have an unlimited amount of time to take it, and it's it's open book, open internet, right? I don't know if it tells you which questions you got right and wrong though after you submit it, but you do get a score. So if you have any issues, let me know. But I just use the quizzes as a way for you to practice and see questions that are similar to the ones that will be on the exam. Okay, right. So pulse width modulation. So the idea with this is that we need to be able to we need a way to control external devices, peripherals. We need a way to control external things that require an analog input signal, like a speaker or a motor, something like that, right? So one way to do that is using a digital to analog converter, which is a circuit that may be available on your chip. I think we do have some on the ESP32. Another way to do it is to just use a purely digital pin, output pin, but you can modulate it with PWM in order to create a sort of a fake analog signal, which is usually good enough for things like motors and even for audio, if you're okay with the audio not being the best quality, right? So this is how like those electronic greeting cards work, like in the grocery store that play a song, right? Uses PWM audio. Okay, so what is PWM? You can also use this for LEDs. This is how LEDs can be brightened and dimmed, right, in LED. Okay, what else? Motors, servos, power electronics. Power electronics are like, voltage converters, that kind of stuff. AC-DC converters, that sort of stuff. Those are controlled by a PWM signal from the ESP32, or from the controller. So what is that? Well, basically, it's just a periodic digital signal, which has it's going to have a fixed period. Period meaning if you measure the time from a rising edge to the next rising edge, that time is fixed, right? Or likewise, falling edge to falling edge, right? So the period is just like in a sine wave, you'd measure, like, say, from peak to peak, right? So the period is fixed, but the duty cycle, which is the portion of the period that the signal is high, that is what's changing. That's the variable part of the signal. Okay, so for example, if you have a 10% duty cycle, that means that the signal is a 1 for 10% of the period, and it's a 0 for 90% of the period. So it kind of looks like a clock signal, except clock signals typically have a 50% duty cycle, whereas a PWM has a variable duty cycle. And the duty cycle is designed to change, right, over time. So as you look from period to period, that duty cycle may be changing. And the analog value that this is meant to represent is the voltage of a 1 multiplied by the duty cycle. So if this is a 5-volt signal and I have a 10% duty cycle, then this is meant to represent a 0.5 volt signal. Does that make sense? Now you might say, well, how does that work? Well, what ends up happening is if you apply a low-pass filter to this signal, right, it ends up looking kind of like the analog signal that it's supposed to represent, right? So in other words, after enough periods go by, on average, it's going to average out as whatever the analog encoded value or modulated value is. Does that make sense? Okay, so this is a 10% duty cycle, 25%, 50%, 80%. 100% duty cycle would just be always 1, and a 0% duty cycle would be always 0, right, DC. Does that make sense? So what is the frequency supposed to, now obviously the frequency is the inverse of the period, but what's the frequency supposed to be? Is there a minimum frequency? That part is a little harder to figure out. Generally speaking, you want the frequency of a PWM signal to be in the tens of kilohertz, right, is the typical frequency you have. But the exact frequency used depends on the application. So if you're using an LED, for instance, like if you're using this to dim an LED, if your frequency is too low, you'll actually see the LED flickering. Like you'll see it turn on and off, right? But you don't want to see it turn on and off. What you want it to appear to be dim or bright, right? You shouldn't be able to perceive the LED turning on and off, in your brain as a human person looking at it, right? So how fast does that need to be? Well, in my experience, usually once you get to like 10 kilohertz or so, you won't see there won't be any perceptible flickering, right, in that LED. You'll be able to just dim it and brighten it, right? You guys have all seen LEDs dim and brighten, and that's kind of the principle, right? It just uses a PWM signal. So what's the advantage of this versus a digital to analog converter, which is an actual analog circuit that does a true digital analog conversion? Well, sometimes that it wouldn't work. Like with an LED, LEDs want to just be on or off, right? So I've never seen a case where someone's actually set an actual analog value to an LED. They always send an on or off to an LED and they just switch. And the same thing goes for a power electronics circuit. Like when you hit the gas on your Tesla, it's sending a PWM signal to the electric motors or to the converter that's sending the power to the motors, right? Because the power electronics are expecting an on or off because they're generally based on a switching converter, right? Like an H-bridge or something like H-bridge circuit, right? So, but then there are other cases where you may want to use an actual analog signal, like if you're looking for high fidelity audio, for instance. Does that make sense? All right. So, so the idea is that conceptually you have some analog signal that you're putting into a modulator. The modulator is converting it to the PWM signal, and then you send that somewhere and it gets demodulated back to the original analog signal. And the demodulator may be explicit or just implicit, like with an LED, right? Okay, so the way that you actually modulate it is, for example, you'll have on the top, I'm showing this sine wave. So this is an analog signal that's varying between 0 and 1. And then to modulate that with PWM, you have to generate a sawtooth signal. A sawtooth is where you basically just have a straight line that goes from 0 to 1 and then immediately back to 0 and repeats, right? There's a sawtooth. So this is not like a shark tooth. This is a sawtooth, right? So it ramps up and then goes resets, ramps up, resets, ramps up, resets. And the period of the sawtooth is going to match the period of the PWM signal, right? So in this case, if this is a 1 microsecond, so 1 microsecond, that's really fast, right? That's a megahertz, right? 1 over a million, right? It's a million hertz, which I don't think I've ever seen a PWM quite that fast, but that's pretty fast. But it doesn't matter. You set the frequency there, and then to generate the PWM signal, really you just have a comparator where you compare for every time step, and time step being, the rate at which you're changing the output signal, you're updating the output signal, the PWM signal. For every time step, you just compare the input signal that you're modulating. If that value is greater than, if that value is greater than the sawtooth signal, or likewise if the sawtooth is less than the modulated signal, so you're just basically just doing this comparison, then you put out a 1, otherwise you put out a 0, right? So you just compare the signal to be modulated against the sawtooth, and then the result of the comparison between the two becomes the PWM signal. So you can see here that the PWM, when you look at it visually, it's sort of course this is compressed quite a bit, but you can see that it's like real dense here wherever you have a higher value signal you're modulating, and it's sparser here, right? Does it make sense? Okay, so we're going to be using PWM in this class in one of our projects to generate an audio signal out of the ESP. The ESP does have digital to analog converters, but we're using the PWM for the audio to see what kind of quality audio we can get out of that. All right, so a question on the quiz might say, what analog voltage is generated with a 3.3 volt PWM signal having a 30% duty cycle? I should have probably said what is the equivalent analog voltage for a 3.3 volt PWM signal having a 30% duty cycle? And the answer there is you multiply, right? So 3.3 volts times 0.3 is 0.99, right? Okay, so let's talk about interrupts. So I mentioned that programmed I/O is fundamentally based on the microcontroller determining when communication is initiated with the peripheral. But if the peripheral needs service from the CPU, or the microcontroller, right? The peripheral, like for example, if it's a network card and it receives a packet, or you hit a key on a keyboard, you need to get the CPU's attention. And this is assuming the CPU is not, polling, not continuously monitoring the situation. They use an interrupt. So in interrupts, did you guys talk about interrupts in 3.13? Okay, good. Yeah, so this is related to operating systems because the operating system is the software that responds to interrupts. In this class, we're looking at this more from a hardware perspective. But the idea is that this peripheral can interrupt the CPU then runs an interrupt service routine, which then deals with the interrupt somehow. And typically, the number of interrupts is often limited. You don't necessarily have a dedicated interrupt for every peripheral. I mean, it depends on the system. But what may happen is if you have, like say one interrupt that covers multiple peripherals, then the CPU would have to interrogate the peripherals to figure out which one, requested the interrupt after the interrupt is serviced. Yes? No, this could be for an OS too. This applies to OSs as well. In this every modern CPU uses interrupts. You don't typically have to deal with them though because you have the operating system does it for you, right? But in bare metal programming, this is something that you may have to be more involved in as a programmer. Okay, so, right. So the idea is that the CPU is running code. The interrupt is requested. The interrupt is usually just a binary signal, at least the component that is signaled by the peripheral. So the peripheral requests an interrupt, and then the CPU sees that interrupt, and it uses hardware to automatically jump to the interrupt handler, right, which is located, either in the OS or at some hardware-defined address. And then it services the interrupt and then goes back to whatever it was doing. When I taught the original version of 611 I taught, we actually implemented interrupt handling in our 611 CPU. We dropped it at some point when we pushed more of the class to conceptual stuff and less to the lab projects. But when we did it in 611, it wasn't too hard to do. You have an interrupt input pin, and when the interrupt happens, you have to, before the CPU jumps to the interrupt, or as it jumps to the interrupt handler, it has to save the program counter address that was in the program counter at the time it jumped. So that basically allows it to return back to what it was doing, where it was prior, right? Okay, so anyway, ISR stands for interrupt service request? Yeah, it's basically the code that services the interrupt, right? So there's some code in there somewhere that typically on bare metal you would have written this, right? Right. Or it might be bundled inside the Arduino library or the API that you're using. Okay, makes sense? So this is how the Atmel 328P handled it. Very simple. Interrupts requests can be level sensitive or edge sensitive. So in this case, I'm showing it as level sensitive. So the CPU is waiting for the interrupt pin to be 1 as opposed to looking for a rising edge. You can also, usually you can configure it to be level sensitive or edge sensitive, right? So you're either looking for the level or the edge there. Yeah, so that's an edge triggered version. All right, so suppose a peripheral is connected to the CPU's external interrupt input. Assume the peripheral can change the value of the external interrupt no more frequently than once every 50 microseconds. Assume the CPU can execute its interrupt service routine, ISR, interrupt service routine. Yeah, that's what ISR stands for, ISR. So assume that the ISR can be run in 75 microseconds. What is the maximum number of interrupts per second possible when using rising edge triggered interrupts? So the idea here is that if you interrupt the CPU really frequently, you can actually live lock it, which means you can deny service to the software that the CPU would otherwise be running, right? You just keep interrupting it, right? And so what I'm basically asking here is, at what point is the CPU live locked? Meaning, what's the maximum rate at which it can service interrupts? Now, obviously, you wouldn't want to do this because it would basically, the CPU would be consumed entirely of servicing interrupts. We wouldn't be able to do anything else. But what is the maximum rate? Okay, well, the question asks about rising edge triggered versus level sensitive, but as it turns out, it doesn't matter in this case because if the CPU, if the interrupt handler can only change every 50 microseconds, that means that the maximum rate it could be changing then is it's high for 50 and low for 50, high for 50 and low for 50, which means the period of the interrupt bit is going to be 100, right? 100 microseconds. And so regardless of whether it's level sensitive or edge sensitive, that's the fastest I can toggle it, right? Make sense? However, if it's level sensitive, I could just leave it high, right? In which case it would just, after the CPU returns from the ISR routine, it would immediately go back. You guys with me? Does that make sense? So I could just, if the interrupt pin is just left high, is just driven high and left there, then the CPU may just continuously run the ISR, right? Whereas if I'm edge sensitive, then I have to toggle it, in which case I'm at 100 microseconds, right? 50 high, 50 low. You guys with me? Okay, so I think I think, so the edge, as I mentioned, with edge triggered, my maximum rate is either determined by the time executing the ISR, which was 75 microseconds. So this is how long it takes to execute the ISR. If I take the reciprocal of that, that's the rate at which I can execute ISRs, right? And then with edge triggered, I mentioned the maximum rate for getting edges in would be 100 microseconds because I'm going to be 50 low, 50 high, 50 low, 50 high, right? And so it turns out that in that situation, the bottleneck here is going to be how fast I'm toggling the interrupt pin, which means the interrupt rate would be 10 kilohertz, right? Right, because basically the CPU is able to get in and out of the ISR faster than the peripheral can toggle the ISR, right? Makes sense? Now, if it's level sensitive, it would be the same thing unless, like I said earlier, you can just keep the ISR, keep the interrupt high, just keep it permanently high, in which case then you'd actually be able to issue the interrupt, then the interrupt kindler could potentially run it every 75 microseconds, right? So this answer could be incorrect if assuming that you could just leave the leave the interrupt pin high, right? On the other hand, if I'm still toggling, if I still have to toggle, then they would be the same speed. You guys with me? All right. So okay. So but that introduces the problem because what happens if I toggle the interrupt pin faster than the CPU can execute the interrupt service routine, right? So in this case, I toggle it here, which causes the CPU to go into the ISR, but then I toggle it again before it finishes the ISR. That may make the CPU miss the second interrupt, right? Because there's no synchronization between the two. Likewise, it's also possible that I may not, the external interrupt may not hold the interrupt high enough in order for the CPU to actually register that interrupt happened, right? You have to, generally speaking, that interrupt pin has to be high for a certain amount of time before the CPU can see it, right? Another possibility is, like I just mentioned, where you hold the interrupt pin high for a really long time, causing multiple ISRs to trigger, right? Because you execute one ISR, you return back to what you were doing, and then the CPU sees that the interrupt is still high, and then it goes back to the executes a second ISR. So in this case, I inadvertently execute two ISRs for one interrupt. In this case, I execute only one ISR for two interrupts. And it all has to do with the timing here, how long the interrupt is held high. So how do you fix that? Well, you have to introduce a handshaking signal. Generally, now the CPU often, this depends on the CPU, but you can have an acknowledgement signal that goes from the CPU back to the peripheral that generates the interrupt. And so that way you can introduce a handshaking protocol where when the CPU issues an interrupt, it is going to hold that interrupt line high until the CPU acknowledges it, which it will know from the acknowledge signal going high, right? And then the CPU will keep the acknowledgement high until it finishes the interrupt service routine, at which point it'll drop the acknowledgement signal, so that way the peripheral knows that it's not allowed to issue a second interrupt until that acknowledgement goes down. Does it make sense? So basically, the acknowledgement tells the peripheral when the CPU acknowledges the interrupt and starts executing the interrupt service routine, but it also tells it when it's finished executing the interrupt service routine by dropping the acknowledgement, right? So you get that handshake. Now, not every CPU has the acknowledgement, and the reason we have this slide here actually is because when we first started teaching this course, we were using the Atmel 328P, which is the 8-bit Arduino chip that is famously probably the most common Arduino chip, or it was. It was the one that was on the original Arduino Uno. That chip did not have an acknowledgement system. So that chip suffered from the problems that you have when you have no acknowledgement, when you just have a one-way interrupt signal, right? The ESP32, I assume it has an acknowledgement system, but I don't even know that for sure. I know that the Neos processor that we use in 313 uses an acknowledgement-based approach. You guys with me? So this all, the point is that this interrupt stuff depends, the way the interrupts work depends on the processor. This is not something that's standardized across every processor type. Okay, so switching gears again. So now let's talk about chip to chip or board to board. Basically external communication. How do we handle external communication? Well, there's lots and lots of ways to do that. They are differentiated by the distance and the performance and the cost. So you guys are all familiar, I'm sure, with PCI Express, right? That's how a typical computer communicates with its peripherals. It's also the underlying technology of Thunderbolt, which is like USB 3. So PCI Express is a very high-speed technology. It used to be that you only had that in a desktop computer. That was the only place you'd see PCI Express. But then over time, it's actually been working its way down to these lighter weight systems. So the Raspberry Pi actually has PCI Express, which is, in fact, people have even taken the PCI Express connection on the Raspberry Pi, and you can connect it to a desktop GPU. Like you can put a full-size gaming GPU on a Raspberry Pi. You just connect it through the PCI Express, which is kind of crazy, but people do it. So PCI Express it's working its way down into lighter weight systems. You also have, I mentioned this earlier in the lecture, but there's also protocols for doing on-chip communication like AXI, which is what you use for peripherals on chip. You might say, what does the ESP32 use on chip? I don't even know. Probably AXI, but I'm not even sure what protocol it uses for on-chip communication. When I was in grad school, there was this protocol called Rapid I/O that was getting popular, but I think it's kind of died out. Yeah, but in this class, we're looking at options that are lightweight, low power, and relatively low performance. So specifically SPI and I2C. You guys might have, some of you probably heard of those already. So those are the protocols that you use whenever you do like Arduino type stuff. And they're very, very popular. I2C is used even in heavier weight systems. If you use HDMI, and maybe even DisplayPort, although I don't know that one for sure. But like when you connect to your monitor, to your computer, there's a communication that goes backwards from the monitor back to your computer, right? And that's I2C typically, right? PCI Express, I think, even has an I2C channel, which is a low speed, like a sideband channel. So I2C is used quite a bit. SPI is really is strictly kind of relegated to these Arduino type systems. And then, of course, there's UART, which we'll talk about too, which is for console I/O. Okay, so bus protocols are divided into different categories, one of which is synchronous versus asynchronous. Asynchronous is when you don't send a clock signal as part of the communication channel. Okay, so some protocols will have data and control signals and a clock signal. And that all forms the channel, right? The communication channel. The clock is used to synchronize. Other protocols don't have a clock. Now, if they don't have a clock, then how do they how do they synchronize? How does that work? I mean, how can you not have a clock? Right? A clock is going to determine when the receiver reads the bits that the master is sending, right? They have to have some kind of clock in common, right? So how can you not have a clock? Well, there's various ways to go about that. So in some cases, you just agree on a clock rate between the master and the transmitter and the receiver. You just pre-agree on a clock rate, and then they just have independent clocks that run at that rate. But that's not great, because the problem with that is, even though both clocks may be at the same frequency, they're not in the same phase. So what may end up happening is that one signal may be, one side of the connection may be changing the data when the other side is reading it, right? So that sort of system only works for low-speed interfaces like UART. And even then, it's going to fail sometimes, which is why you have to have some kind of error detection mechanism if you do that, which UART has, called parity. Another approach is if you have a high-speed connection like PCI Express. How's PCI Express and SATA and HDMI work? They use a technique called, they use an encoding technique where the data is sent, but it's encoded into more bits than you actually are sending. So for example, they have 10-bit, 8-bit encoding where you put every 8 bits goes into 10 bits. They have another one called 66, 64-bit encoding. And the objective there is the encoding is set up to where you maximize the number of transitions that you send, right? So this is designed for serial protocols. So like if you have a 10-bit, 8-bit encoding and you're sending just zeros, right? Say you're just sending zeros. That 0 is actually encoded as 10 bits where it's not all zeros. There's actually transitions. And that allows the receiving side to use a circuit called a phase lock loop to extract the clock signal from the data. It can figure out what the clock is based on the data, assuming the data is going from 1 to 0 and 0 to 1 frequently enough. Does that make sense? So that's another way. Those are just two ways that you can do asynchronous. But the point is that in order to do an asynchronous channel, there has to be some trick involved, right, in order to take care of the clock. Okay? And of course, synchronous is when you just have a clock. Okay, so let's look at some examples here. So, another thing too is, right, there's a few other ways that you can distinguish these protocols. So some protocols can only have one sender, one initiator. Right? That's called a single master type bus, right? Other buses, when I say bus, I mean communication protocols. Other communication protocols can have multi-master, where you can have more than one entity that's allowed to speak, right? Do I have any other distinction here? Yeah, so that's the other distinction. So we have synchronous and asynchronous and single master, multi-master. Okay, so let's talk about SPI then in this context. So SPI stands for Serial Peripheral Interface, and it is one of the protocols that that you'll see if you do any kind of lightweight microcontroller work. Now one thing though, I want to make one thing clear here is that if you're buying parts and just building a system and you're using the APIs, you don't necessarily need to know how SPI works, right? You just in fact, most people that do this kind of stuff don't, right? You just buy, you buy an Arduino and you buy an accelerometer, and you know the accelerometer supports SPI, and so you just connect the wires, right, from the accelerometer to the Arduino, and it just works, right? You don't have necessarily, may not know what's going on under the hood, right? So, but it's important to, I think it's important to understand how these things work. So that's why we're covering the actual nuts and bolts of the protocol here. So an SPI channel is, and you can have multiple channels, you can have multiple connections, but each connection, every channel, is actually comprised of four wires. Clock, and then you have MOSI and MISO and SS. So clock is the clock. So obviously this is a synchronous protocol because it has a clock. And then you have MOSI and MISO. MOSI is master out, slave in, and MISO is master in, slave out. So basically these are just the data, and the data is full duplex, which means that you can send and receive data at the same time because there's dedicated wires for each direction of data flow, right? And the fact that you have a master and slave indicates that this is a master-slave style interface, much like programmed I/O is, where the CPU or the controller is the master. It initiates all the communication, right? And then there's the slave side is usually the peripheral or the I/O device that just responds. And then SS stands for slave select, which is essentially just a bit that turns on. It essentially just turns on the channel. It's when it's asserted when you do communication. It's deasserted when you're not communicating. Okay. Okay. So SPI was originally envisioned as a way to perform an exchange of data. So every time you initiate an SPI communication, you're taking a word, in which case, in SPI, by the way, a word is considered 8 bits. This is a little confusing because remember, ESP32 has a 32-bit word, but SPI communication is done in units of 8 bits, right? So you take an 8-bit word and you send it from one entity to the other, and from the other entity back. So you do an exchange, right? The master sends 8 bits, the slave sends back 8 bits, right? And because it is a serial protocol, you can think of it like a shift register, where the bits get shifted out of one side and they get shifted in the other side. So it becomes this like circular shift register. And so because there's 8 bits that are being exchanged, it takes 8 cycles to perform the exchange. Make sense? So you just do an exchange. And so the MOSI goes from the master to the slave sends back MISO. Okay, now one of the issues with this is that it's almost never the case that you want to do an exchange. Like whenever you do communication, what are you doing? You're doing like, I want to read an acceleration from the accelerometer, or I want to read something from a sensor, right? Am I exchanging? No, I just want to read data. I don't want to exchange data. I want to read a data from a sensor. Or if you have an actuator, I want to send data to the actuator, right? I don't want to exchange. So this idea of an exchange is kind of dumb. And in practice, no one ever does the exchange, right? It's usually just one-way communication, right? But the protocol still is designed around this idea of an exchange. Okay, so keep that in mind. That's part of the confusing part of SPI.
But it takes n cycles to change that.
Yeah, exactly. So 8 bits would be 8 cycles. Now you could exchange more. You could do 16 in 16 cycles. It's always in multiples of 8, though, as far as I know. Okay, so now the other problem with SPI that makes it a bit difficult is SPI fixes some rules and then it leaves other rules up to the user. So one of the rules that it fixes, that's always true, is that the slave select is active low. So slave select is a 0 whenever there's active communication happening on the channel, and it's a 1 otherwise. So that you can't change. However, there are some things that are changeable. The first is the clock, what the clock is doing. The clock only operates during communication. Otherwise, the clock is idle, right? So in other words, you're not constantly toggling the clock all the time. This is designed to save energy, be more power efficient, right? So the only time that the clock is going is when you have active communication. However, the clock can either idle at 0 or at 1, and that depends on a parameter called CPOL, which stands for clock polarity. If the clock polarity is 0, then the clock has to be 0 when the channel is idle. If the clock polarity is 1, the clock has to be 1 when the channel is idle. Why is this just not always, fixed? Why isn't it always one or the other? I don't know. There's some kind of historical reason for this, I'm sure. Yeah. I don't know what it is, though, right? Now, another thing is, and this is the one that's a bit more confusing. So you guys remember from 611, and hopefully you covered this in 311. When you have a clock in a digital circuit, generally you're using the edge of the clock, right? You're triggering things on the edge. The flip-flops read on the edge of the clock. They're edge triggered, right? Make sense? Now, level triggered would be like a latch. Edge trigger would be a flip-flop, but everyone uses flip-flops, right? Latches are fairly rare, right, in digital circuits, right? In SPI, we assume that the clock is edge triggered, meaning that the receiver, whoever is receiving the data, reads the data on the edge of the clock. Okay? And the idea is that we want the sender to change the data on the other edge of the clock. So when I send data on SPI, I change my data bit on one edge, and the receiving side reads it on the other edge. Right? Why is that? Well, that's designed to avoid the case where I change the data and the guy is reading the data at the same time, because then you're reading data that's sort of in a state of transition, right? You don't want that, right? Make sense? Okay. The problem is that the edge of the clock that we want to read the data on is also a parameter called CFA, clock phase. Right? Why? Again, I don't know. It's a parameter that both sides of the connection have to agree on before they can talk to one another, right? Now, in the case of the ESP32 and in the Arduino, generally the way this works is you have to read the data sheet of the peripheral that you want to talk. So you buy a peripheral, right? You go to the store, you buy a chip. Chip says, I do SPI. And you say, good, because I have a spare SPI channel on my controller. But then you have to read the data sheet and ask and figure out what the clock polarity and the clock phase of that controller's SPI channel is. And then you have to go to your Arduino or your ESP32 or your STM32 chip, and you have to tell it what those numbers are, what those values are. Otherwise, they can't talk. You guys with me? So generally, the CPOL and CFA is hard-coded in the peripheral, but it's programmable in the controller. Controller being your CPU chip, right? Make sense? Okay, so to make things even more complicated, the CFA is not, it's not like, okay, rising edge is 0, falling edge is 1. No. The CFA is defined relative to the first clock edge during a transaction. Okay, so bear with me here a second. So if CFA is 0, it means that I am going to sample, as a receiver, I'm going to sample the data sent to me on the first edge of the clock. If CFA is 1, I'm going to sample it on the second edge of the clock. And when I say first and second, I mean during a transaction. During an exchange. Right? Now, what is the first edge and what's the second edge? Well, that depends on the polarity. So if the clock polarity is a 0, the first edge of the clock is going to be rising edge, right? Because it starts 0, it goes high. And the second edge is falling. If the polarity is 1, the first edge is falling and the second edge is rising. You guys with me? Does it make sense? It doesn't make sense, but it's how this protocol is designed. It's kind of insane. In fact, it really surprises me that anyone still uses SPI. But it's still very, very popular. Okay. All right, so here's an example of an exchange. Now, one of the things I like about this material is you get used to having to read a timing diagram. Although you guys did a lot of this in 611 already too, when you simulated your CPUs. So a timing diagram, as I'm sure you remember, is meant to look like an oscilloscope or a logic analyzer output, where the horizontal axis is time, and then the vertical axis is meant to represent 1 or 0, right? For a binary signal. So when you perform an SPI exchange, obviously you got 4 signals. If C-pole is 0, sorry, C-pole is 0. If C-pole is 0, that means the clock starts out as 0, because when you're not actively using the channel, the clock is always 0, right? That's the idle state of the clock. When you want to initiate an exchange, the master sets slave select low, right? At which point the channel becomes active and you start to clock up. How many clock cycles are we doing here? 8, right? Because there's 8 bits. It's a bit serial protocol, so there's 8 cycles, okay? But the thing that's weird is the timing here. If C-fa is 0, then I'm expecting to read each bit starting from the first edge of the clock, which is here. The first edge of the clock is going to be a rising edge because C-pole was 0. The clock starts out as 0, so the first edge of the clock has to be a rising edge, right? So I start with the first rising edge, and I read the data on each rising edge, okay? That's the receiving side. The sending side is going to change the data on the falling edge of the clock. You guys with me? So the data changes on the falling edge, but it's meant to be read on the rising edge. That way, you might say, what is the point of all this? The point is so I want to try to make the channel as robust as possible, right? I don't want to risk. I want the data to be stable for as long as possible before and after I read the data. Why? Because of setup and hold time. You guys remember setup and hold time from 611? Setup and hold time says that you have to have a stable input prior to the clock edge, right? That's the setup time. And the hold time is you have to have the data has to be stable after the clock edge, right? So in order to guarantee that there are no setup and hold constraints, I want to maximize the stability time around each change. Around each sample, I should say, right? So I change it here, I change it on the one edge, and I read it on the other edge, right? And the C-pole and C-fa together are what is going to determine essentially what edge I change the data on. Yes? Exactly, yeah. Falling edge change, rising edge read. Okay, now you might say, wait, why do we need 2 signals for that? I mean, why not just have 1? Well, the thing is notice one of the things that's crazy here is that the first time the data is changed, there's actually no falling edge on the clock. Like normally the data is changed on the falling edge, right? Right there, right there. Like every one of these dotted lines shows where the data changes and it corresponds to the falling edge. But the first time, there's an exception here. The first time, there's no clock edge the first time the data changes, right? So what that means is that the data has kind of a head start on the clock here, right? But this happens only when C-fa is 0. When C-fa is 0, the data has to already be established before the first edge of the clock. right? Does it make sense? And there should be 8 cycles, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there's always 8 cycles. Okay, and then now keep in mind too that MOSI and MESO are both changing at the same time, right? Right, they both change on the same edge of the clock, which means that the changing and the sampling edge of the clock is done on both sides of the connection, right? It's okay. Now let's look at another example here. So that's this one. What happens if C pole is 1, CFA is still 0? In this case, it's the same idea. The only difference is that the clock starts out as 1. The first edge of the clock is falling. You still get a half a clock cycle head start here on MESO and MOSI, right? So basically, C pole and CFA are the when you change. I'm sorry, when you change C pole while keeping CFA the same, the only thing that changes is the clock is inverted, right? Now, if I change CFA to 1, the CFA 1 means that I'm going to read the data on the second edge of the clock, which means that the data will change on the first edge of the clock, right? So when CFA is 1, check this out. The clock, C pole is 0, so clock starts out as 0. The first edge of the clock is a rising edge. The data changes on that rising edge, but it's not read until the next falling edge, right? Which means that if CFA is 1, the data doesn't get that head start ahead of the clock. It changes on the first clock edge. Does that make sense? So what does this all mean? Well, basically, CFA, the only difference that CFA makes is that the data gets shifted by half a clock cycle. Right? That's the only difference. The timing of the data is shifted 1 clock cycle into the future, ahead, to the right, right? That's really the only difference. However, it makes that there's a huge impact of that, though, because if you set this up wrong, you'll end up, in the best case, you'll be off by, basically, your data will be shifted by 1 bit. The data you read over SPI will be shifted by 1 bit. But the worst case outcome is it could just be totally garbled, because every time you read, you're also writing. You're writing and reading the data at the same time. There's going to be a violation of the setup and hold time. You could end up with random errors, right, due to metastability on the flip-flop, reading the data. Does that make sense? So this is all designed to make sure that you avoid reading and writing the data at the same time. That's really what this is all about. The problem is that it's needlessly complex because the timing is determined by a combination of the C pole and the CFA. All right. Okay. So here's an example question I might ask. In the following SPI exchange, what is the value that is sent from the slave back to the master? So in that case, we're doing MESO, right? I always get these confused. Master in, slave out. Yeah, this would be MESO, right, in that case, right? So this is the, now, by the way this works is that the master side controls SS, S clock, and MOSI. And the MESO is the one that's sent back, right? So basically, if I'm the ESP32, these top 3 are my outputs, and the bottom one here is my input, right? This is a feedback signal that comes back, right? And so I have technically the ability to do full, bidirectional data transfer, right, on both sides. Every cycle, bidirectional. I will send a bit, I receive a bit, right? Okay, so if C pole is 1 and CFA is 0, that means that CFA, I'm sorry, I said that wrong. If CPOL is 1 and CPOL and CFA are both 1, CFA being 1 means that the data does not get a head start on the clock. The data starts changing on the first clock edge, which you can see it does, right? The first clock and the data are lined up. But I have to wait to the second edge to read. So I'd be reading on the rising edge. Okay? So notice that in this case, this works out very well because these dotted lines just happen to intersect the rising edge of the clock. So if I want to interpret the data, I just have to figure out where MESO intersects each dotted line, right? So that's pretty easy, right? 1, 0, 1, 1, 0, 1, 0, 1. Right? Just look at the intersection point. Now, sometimes, though, you may find that, depending on the timing, the dotted lines may not line up that way, right? But in this case, it just happens to be that the dotted lines are the sample point. So, yeah, there it is. It's, again, it's, now in this case, I put my own dotted lines here where the data changes, meaning that if you read between my red dotted lines, you have the data, but you can also just look at where the dotted lines here on the timing diagram intersect. It just depends on how you want to read it. But again, 1, 0, 1, 1, 0, 1, 0, 1. Okay? So those are the bits. The problem is that what order do I read those bits in? Is it most significant to least significant or least significant to most significant? In other words, is this bit 1 or is this bit 7? The first bit. Well, according to this, it says most significant bit first. I think SPI generally uses MSB first. But just for clarity, I always explicitly list that, right? Okay, so what does that mean? Most significant bit first? Well, that means that this is bit 7, so pretty much I can just read this out in the same order that it's shown in the timing diagram. So hexadecimal-wise, this is 1011, which is what? 8 plus 3 is 11 is B, right? B. And then this is 5, which is 5, so B5. Right? So B5 is what is coming back on the channel from, from the peripheral back to the CPU. Okay, here's another, what's the value sent for the master of the slave? This is CPOL and CFAR 0. So in this case, CFA 0, so notice that the data gets a little bit of a 1/2 cycle head start. I can read on the first edge of the clock. The first edge of the clock happens to be rising edge because CPOL is 0. So here, and I'm looking at MOSI, so here it's 1, 0, 1, 0, 0, 0, 1, 1. And again, it's most significant bit first, so it's going to be 1, 0, 1, 0, which is 10 or A in hex, and 0, 0, 1, 1, which is 3, so A3. Okay? All right. Okay, so I mentioned earlier, I alluded to this, but who wants to do an exchange? Why would we ever do an exchange? Why do we need to have simultaneous data flowing in both directions, right? I have never seen anyone actually use that with SPI, by which I mean, usually, if you look at MESO and MOSI, usually one of them is dead. Usually one of them is not being used. Right? Usually you only use one at a time. You just need, generally, application-wise, you only need to send data in one direction at a time, right? Not in both directions. So that is when we may differentiate this idea of an exchange. So every 8 bits technically does an exchange, right? But we need to build a transaction level protocol on top of SPI that can be used to perform programmed I/O style access, right? Now remember, programmed I/O, what is that? It's a load or a store, right? Load or a store, unidirectional. If you load, I'm reading. If I'm storing, I'm writing. I'm never reading and writing at the same time. In fact, CPUs generally don't have instructions that can do that, right? You can do a load instruction, you can do a store instruction. They're unidirectional, half duplex, right? Now, you guys might remember, though, that on the RISC-V CPU in 611, there was actually an instruction that did a simultaneous read and write. It was called the CSRRW instruction. Remember that? Which we actually only used it, we actually hacked it to make it not do that, right? Technically, there are some instructions, like, for example, atomic exchange. You might have heard about that in operating systems. In 311, there's an atomic exchange instruction that reads and writes at the same time. But typically, when we do peripheral I/O, it's unidirectional, right? And we call those, call those transactions, right, usually. A read transaction, write transaction. Also, the other problem is you might have noticed that this SPI protocol, there's no address. There's just data. There's no mention of an address anywhere in here. When you do a read or write, or a load or a store, usually there's an address and there's data. So I read from an address or I write to an address, right? I need address, I need data. So how do you figure we can get SPI, given that this is how it behaves, how can we make it adapt to a transaction level protocol where I have an address? How's that going to work? Well, you have to hack it, essentially, and the way it's hacked is you do 2 exchanges, meaning instead of 8 bits, you do 16 bits, right? If you write, you send the address in the first 8 bits, and then you send the data that you want to write in the second 8 bits, right? Which means that you only use MOSI, but in the first part, you do like a header, essentially. It's kind of like a network packet where you have a header and a payload. The first 8 bits is the address, the second 8 bits is the data, but they're all sent through MOSI because I have to send the address to the peripheral and I have to send the data to the peripheral. But if I want to read, in other words, a load instruction or programmed I/O read, I send the address in the first 8 bits, and then I expect the peripheral to send its data back in the second 8 bits, right? Which means that in the first exchange, I only use MOSI to convey the address. And in the second exchange, I only use MISO to get the data back, right? That assumes, by the way, that the peripheral is ready to send the data back on the ninth cycle. Yeah? Yes? Well, then you have to define a new transaction protocol that uses 2 bytes for the address, right? Which you can do.
But that's not SPI.
No, it's still SPI. So I think the reason why SPI, one reason why people may still be using it, even though it's so hacky and ad hoc, is because it's not standardized. It's not governed by a standardization body like a lot of other protocols are. It's like it's almost like it's not really an official standard as far as I know, right? So you don't have to worry about adherence, right? You don't have to be compliant with a protocol, right? I²C, which is the other protocol we're going to talk about, is governed by like a standards body, whereas SPI is not. It's like a Wild West. So you can hack SPI. You can define your transaction protocol to be whatever you want. You're not limited to whatever to whatever the man wants you to use, right? You can do whatever you want, right? All right, so that's all we've got for today. I'll hopefully finish up this stuff on Thursday. Thank you.